So last time I wrote an equation for the electric field. Let me remind you of the setup. We had some charges, Q1, Q2, Q3, Q4, and we brought a test particle here. And we looked at all the forces acting on the test particle, right? We said that one puts a force on the test particle, so that force goes along this line. It's the force of one on the test particle. Two does the same thing, so you can draw a line along those two particles. The force is going to be attractive or repulsive. So let's say that in this case is attractive. So this is the force of 2 on the test particle. Then we have 3, which is over here. And let's say that that force is repulsive, so it's a vector like this, 3t. And finally, number 4, it's a force that acts along this line, and let's say again that it's repulsive. So 4t. So what we did was we wrote that force, the equation for the force. Let me start with that one. So the net force acting on the test particle, we said that was the Coulomb force for each one of those pairs, 1 with test, 2 with test, and so on. So K, Q1, Q test over R, distance between 1 and the test particle, square. And then we wrote a unit vector here that tells us the direction of that vector. A, Q2, Q test divided by R2T square, R2T unitary vector, and Q3, Q3, Q test divided by R3T square, unitary 3T, and the last term 4QT over R4T square, unitary 4T. That's what we wrote, right? And then we said, well, if I suppose that the charges are here in this room and I have my test particle here, I calculate the force, I spend some minutes calculating this, taking care of all the different directions, adding the vectors with components, component by component. I'm done with that work, and then somebody else walks in the room, stands at the same place where I was, but they're holding a different charge, a different test charge, right? They also want to test the field in this room. So do they have to go through the same calculation? The answer is no. You can factor from this calculation, you can factor the charge of the test particle, because it shows up in every single term here. And everything else, you give it a name. Everything else, we're going to call it the electric field. There, R3T square, unitary 3T, plus Q4 over R4T square, unitary 4T, and I'm done. So this whole thing is what I call the electric field. Me and everybody else. So this is the electric field. I'm going to write it a better way here. Okay, this is the equation that tells us the connection, or this actually defines what electric field is. So it's the force on a test particle with charge Q test located at some place in space R. So you have Q1, Q2, Q3, and as many charges as you have. And you're over here and you put your Q test right there. I'm gonna define an axis here, set up a coordinate system, right? And this guy, the Q test, is located by the vector r, right? All the little r's in that equation, the r hat, 1, t, and so on, were vectors pointing from 1 to test, from 2 to test, and so on. So they will be here pointing somewhere, right? So what this equation is saying is the following. The force on a test particle that has been located in a point in space, whatever point in space it is, located by, specified by r, is equal to the amount of charge that you put in that point in space, Q test, multiplied by this quantity, which is the electric field produced by the sources. In this case, the sources are Q1, Q2, Q3, Q4. Those are your sources. And the vector E points in a particular direction in space at that point r, specified by r. It's a vector and it points in a particular direction, right? So this quantity, E sources, is produced at some point in space r by the source charges. So the source charges in this interpretation, the source charges are affecting space. Every point in space has been affected by these source charges. It's been given a quantity, a property. Every point in space has been given a property, right? And when you bring a test particle to that location, it feels that. Okay? Now up to this point, I have justified doing this by saying, look, it's convenient computationally. You just have to, you choose a grid of points in this room, you have charges in this room, you choose a grid, right? You compute at every point the vector E, right? Vector field, and you're done. Every time you bring a charge into this room, you know exactly what's going to happen to that charge. That's your test charge. Because at that point in that grid, you know that the vector E is pointing in this direction. You multiply by the amount of charge, and you're done. That's the force, right? So I said it was a good, important computational tool. But the question then is whether there is any real, if this electric field is somehow real, or it's just a mathematical thing that we use for convenience. Right? That would be a question that you might have in mind. Well, the answer is that E is as real as you and me, and E is what you really need to use when you're talking about, when you're trying to calculate the interaction between two charges that are moving. If the two charges are not moving, if Q1 is here and Q1, Q2, Q3 in this room are static, located someplace in this room, and I bring a charge here, and I know I just leave this charge here, then you're fine using Coulomb force, right? And you can think of the electric field as just something that helps in the computation, right? But when you have two charges that are interacting and these charges move, Coulomb force does not give you the right answer. So think about the problem of the system of the sun and the earth, right? Suppose that from somewhere in the universe there is this massive black hole that is being shot at the sun. It's moving really fast, we don't see it coming, it just comes quickly, grabs the sun and takes it away, right? So what is the earth going to do? Will the earth immediately get loose, losing the gravitational interaction with the sun? It would just start moving in a straight line? Or would it continue to move for some time at least in a circular trajectory? The question has to do with what I just said, right? Because if you say that the interaction between the sun and the earth is given by, and you know this from high school probably because we didn't cover it last semester, if it's given by g times the mass of the sun times the mass of the earth divided by the distance between them squared, which is the same as Coulomb equation, right? Then that is telling you that the interaction between the sun and the earth is instantaneous. If you make the mass of the sun go to zero, disappear, then the force on the earth should disappear immediately, instantaneously. So instantaneously you would get the earth moving in a straight line instead of in a circle, right? But if there is some reality to fields, then the gravitational field, which is the same definition as the electric field, that is the gravitational force on the earth divided by the mass of the earth, so the earth is like the test particle, then if you disappear the sun, the gravitational field might take some time to carry the information from the sun all the way to the earth, right? So that is the case, and because light takes 8 minutes to go from the sun to the earth will continue to move in a circular trajectory for 8 minutes. And then it suddenly would find that there is no gravitational field anymore, and it will move in a straight line. Now more dramatic will be the case for Pluto, because Pluto will take 5 hours to find out that the sun is gone. So it will continue moving in a circle for 5 hours like nothing happened, and after 5 hours, just shoot straight. Okay? So with electrical charges, it's exactly the same situation. You have two charges, you suddenly move one, you grab charge number one and you move it, you shake it. Number two is not going to notice that instantaneously. It's going to take an amount of time that's equal to the speed of light, to the distance divided by the speed of light. After that amount of time, this one is going to feel what's happening to this other one. Okay? So if the two charges are not moving, you're fine with Coulomb. Q1, Q2 divided by the distance squared, you're fine. But if one of them is moving, what is real and what allows you to calculate correctly the force on this particle is a calculation of the electric field. Okay? And that was the big step that Maxwell did in 1867 when he wrote Maxwell's equations, which refer to, it tell you how to solve for the electric field and the magnetic field. He said these things are the real things. This is what you need to compute. And those equations tell you precisely that a perturbation in the field in some place in space takes an amount of time to arrive to other point in space. Where is that? So I want you to keep a mental picture of an electric field, because this is an abstract concept. It's invisible. It's hard to think about the electric field. Visualize it, but this is the picture that I want you to keep in mind. It might be helpful for you. You might have seen meteorological weather maps. Say this is Texas, this is Houston over here. And the weather map tells you the temperatures, right? In this area, these lines, different colors represent different temperatures. But more detailed maps also will give you information about the wind speed, the wind velocity actually, not just the speed. So in those maps you will see little arrows pointing in different directions. Every arrow means, or represents, the wind velocity at that location, right? The bigger the arrow, the stronger the wind. So the number given will be winds of 65 miles per hour, right? Northeast winds 65 miles per hour. That means the wind is coming from the northeast direction and is blowing at 65 miles per hour, right? So all of these vectors are telling you the wind velocity at different locations in space, on Earth in particular. So if you had a little sailboat here, the force that that sailboat would experience when it is at this location on the Gulf coast, on the Gulf, will be given by how strong is the wind blowing and in what direction is the wind blowing, right? The force on that boat is going to be proportional to the size of the area of the sail, right? The bigger the sail, the more the force on that boat, right? But also it would have to do something with the wind velocity. This is the velocity of the wind. So what is the analogy that I'm trying to give you here? The wind velocity is our is what? Over here. The electric field, right? The area of the sailboat would be equivalent to the charge of the test particle, right? You put your boat at this location, the ocean, and because the wind is blowing in that direction and with that strength, then the net force on that boat It's going to be in that direction, and it would depend on how big is the sail, and of course how strong is the wind blowing. So imagine the electric field produced by charge 1, 2, 3, and 4 at any location in space as sort of the resulting wind produced by each one of these charges. It's sort of like each charge is blowing out, producing wind, blowing out air in all directions. It could be sucking in air if it's a negative charge. We'll talk about that in a minute. But the wind direction at this location is the superposition of the wind produced by that charge over there and the wind produced by that charge over there. And at a specific location in space, the wind has a velocity. That is the electric field. It has a magnitude and it has a direction. If you place a particle at that location, that electric wind is going to push the particle with a certain force in a certain direction, given by that. So the wind velocity is something that is a property of the space. Right? At every point in space, I have assigned a vector that tells me how hard is and in what direction is the wind blowing. So it is a property of space. The force is a property, or is something that acts on a particle. It's a combination of the property of the space in which the particle has been placed. The force on this boat is a property of the point on the ocean where you place it, and it has to do with how big is the sail of the boat, of course. No sail, no force. Bigger sail, bigger force. So no charge, you don't feel the electric wind. Big charge, you feel a strong force coming from this electric wind. Okay? So particle A and particle B, just to emphasize that, they don't really interact with each other. What particle A is doing is interacting with the electric field, producing or modifying the space surrounding it, giving that space a particular property, some sort of wind, electric wind at each location. And what happens when you bring a particle B in the neighborhood is that B interacts with the electric field produced by A. B interacts with the electric field produced by A. Right? Sort of like two boats, right? And one is producing waves, the other boat feels those waves. This boat is not really shaking this boat directly. It's doing it indirectly through the water. So particle A and B are influencing each other, but through the electric field. So we normally think of space as nothing, right? When you think of a point in space, out there in space, if there is no matter in it, you think that there is nothing absolutely there, it's nothingness. But the picture that we get from physics, starting with this idea of field, is completely different. The space, a region of space, has properties, right? It can have an electric field in it, right? That region of space could be stretched. General relativity tells us that the mass of an object modifies and stretches or contracts the space surrounding it. So from general relativity, from Einstein's theory, we know that space has a shape, that space can be contracted or it can be extended, it can even be twisted. Regions of space might be twisted due to matter in the nearby. And from quantum mechanics, we also know that any region of empty space, empty quotation mark, has actually an immense activity of particles being created and destroyed constantly. It's like a little sea of particles doing all sorts of crazy things. And one of the things one of the properties that space has is the possibility of having an electric field in it. And that electric field, when you bring a particle at that place, you will feel it. A charged particle, that is.